So we're going to go through the Chapter 2, Part 1 review test. I just wanted to make sure that we were all on the same page with what were the topics that we covered so far in Chapter 2. So we're covering average and instantaneous rate of change, finding limits using a table, properties of limits, techniques for evaluating limits, right-hand, left-hand limits, and limits at infinity for vertical and horizontal asymptotes. Okay, so with that in mind, let's take a look at our first problem. So a ball dropped from rest at time t equals 0 travels a distance of 4.9 t squared meters in t seconds. How far does the ball travel during the interval? So what we're going to do is I want to find the change in s. So the change in s would be s of 2.5 minus s of 2. So that is 4.9 times 2.5 squared minus 4.9 times 2 squared. When we type that into our calculator, we get 11.025 meters. So to compute the average velocity over that time, we're going to take the change in distance over the change in time, and that's average velocity. So average velocity would be 11.025 meters divided by 2.5 minus 2 seconds. And if we again type that into our calculator, we're going to get 22.05 meters per second. So last one, estimate the instantaneous velocity. So we could look at a table because what we're looking at is the limit as t approaches 2 of 4.9 t squared. So we could look at a table, but we also know how to evaluate this function. First off, we see if we can just plug it in. So 4.9 times 2 squared, which will give us 19.06 meters per second. All right. Number 2, why can we only estimate the instantaneous rate of change rather than actually calculating it? And we came up with this reason because instantaneous is at a singular point. So because instantaneous occurs at a single point, and we use limits to find it. All right, number 3. Fill in the table for this following function. So if we take out our calculators, make sure it's not in glare. Got my calculator out, and I'm going to go to a new document. I'm going to add a graph, and I'm going to type in our function. So I'm going to make our division symbol, and we want x to the third minus 1 all over x squared minus 1. Now, here's our graph, and we want to fill this in as we're getting closer and closer to, it looks like 1. So I'm going to hit Control T to pull up a table. I can see at 1 I'm undefined, which is what I know. So as long as something's highlighted over here, I'm going to hit Menu, go to Table, go to Edit Table Settings, and I'm going to change my independent to Ask. So once I have that, now I can start typing in my data. That's 3 zeros. And then 1.000. So if I type all of this in, I'm just going to fill in this table now. I've got 1.501, 1.50075, 1.50037, 1.50007. And then likewise, if I did for these, I would get 1.4985, 1.49925, 1.49962, and 1.49999. So we can say the limit of our function as x approaches 1 is equal to 3/2 or 1.5. Next up, estimate each limit. So the limit of sine of 2x over x. Well, we don't know we know sine x over x, but we don't know what 2 sine x is. So I'm going to use my trig identity, and that's 2 sine x cosine x all over x. Now, what I can do, using the properties of limits that I know, that's 2, the limit times x as x approaches 0 of sine x over x times cosine x over 1. These are equivalent statements. The limit as x approaches 0 of sine x over x is just 1. And if I plug 0 into cosine, that's also 1. So I'm left with 2 times 1 times 1. So my answer is 2. Next up, first step, plug in 3. I get 0 over 0. So how could I do this relatively quickly? Well, if I can factor the bottom, which is x minus 3, x plus 1, I know that one of these is going to cancel. My guess is x minus 3, so I'm just going to do a quick synthetic division over here. 3 on the outside, 1, negative 2, 0, negative 9. Bring down the 1, 3, 1, 3, 3, 9. So that leaves me with x minus 3 times x squared plus x plus 3 all over x minus 3, x plus 1. Now my x minus 3's cancel, so the limit as x approaches 3. I can plug this in. I get 15 over 4. For C, first step, plug in 4. I get 1 over 0. So we will say this is a limit that does not exist. And if I wanted to, I could look at the limit as x approaches 4 from the left, which is negative infinity. We can do this from a graph just to save time. And then limit as x approaches 4 from the right is equal to positive infinity. So these two don't match up. That's why we say our limit does not exist. All right. 5. Evaluate each limit, assuming that f of x equals 3 and g of x, limit as x approaches 4 of g of x equals 1. So if we multiply two functions, we multiply their limits. So that's as easy as that. 3 times 1, which is 3. If we have multiples or if we're adding them, we're just going to do 2 times 3 plus 3 times 1, which is 6 plus 3, which is 9. All right, flip it over. All right, so the flip side, we have more limits to do. So first things first, I'm going to plug in 3, see what happens. If I plug in 3, I get 0 over 0, which tells me I have to do work. So my guess is this is a divisor. So again, just like we did on the front, we're going to do a little synthetic. 1, negative 3, 1, 0, negative 9. So bring down the 1, 3, 0, 0, 1, 3, 3, 9, 0. Okay, so that drops that down, which means I have x minus 3, the limit. So x approaches 3. X minus the parentheses, x cubed plus x plus 3 all over x minus 3. These cancel. So now I can plug in 3. I get 27 plus 3, which is 33. So the limit as x approaches 3 of this is 33. Next up, this is the difference of 2. So I messed up. This is the difference of 2 cubes. So if I factored that, first, it shouldn't be 0 over 0, because if I plug in 8, I get some number over 0. Some number over 0 means the limit does not exist. Sorry about that. Next up, number 8. So again, let's see if we can do this right this time. We're going to plug in 1/2. I get 0 over 0. So now I'm left with doing some work here. So that is 2x plus 1 will stay the same on top. Now my guess is I can factor this. So this is 2x plus 1 and then x plus 1. So once this is factored, my two things cancel out. I have the limit as x approaches negative 1/2 of 1 over x plus 1, which gives me 2. Next up with number 9. Again, if I plug in 0, I get 0 over 0, which means I have work to do. So this is the limit as x approaches 0 of 4t plus 1, 4t minus 1. This is the difference of two perfect squares. It just looks a little different. So now these two cancel out. If I plug in 0, I get 1 plus 1, which is 2. All right, next up. I'm looking at the limit as x approaches infinity. Okay, so when the numbers get really big here, this is basically looking at the limit x approaches a big number of x squared over, well, if we take the square root of x to the 4th, that's just like saying the absolute value of x squared. Well, the absolute value of x squared is always going to be positive. We can't get a negative number out of here, so that's really just x squared over x squared, which is 1. Hopefully we can see the logic behind that. Next up, the limit as x approaches negative infinity of this guy. So what happens when we plug in really, really large negative numbers? If we know our graphs, this is when the numbers get really large, we can approximate this end behavior to just x to the negative 5th. And x to the negative 5th looks something like this. So if you plug in numbers really negative, you're going to get out positive infinity. So that's 11. 12, plug in infinity. Well, I can't really plug in infinity. So I'm going to look at, well, what's the degree of the top? The degree of the top is 1. The degree of the bottom is 2. If I know that the degree of the numerator is less than the degree of the denominator, then this just goes to 0. All right, one more page and then we're done. All right, given this function, tell me what's the limit as x approaches 0 from the right of f of x? So from the right, as I approach 0, that would be 4. If I approach 2 from the left, that would be 1. If I approach 2 in general, these two numbers don't come out to be the same, so that does not exist. The limit as x approaches 2 from the right is 2. The limit as x approaches 4, both approach 3. The limit as x approaches 5, which is just 1. And f of 5 is 5. All right, last up. Both of these problems, I want you to use a graph, because that's the only way we can really tell. So, if you do these by graphing, and you say the limit as x approaches 0 from the right, if you look at the graph here, from the right, it's going to go approach 1/6. From the left, as x approaches 0, from the left, you get infinity. If you graph these, you'll be able to tell. Same thing. If you look at a graph here, the limit as x approaches negative 2 from the right, you get negative infinity. And if you look at the limit as x approaches negative 2. From the left, you get positive infinity. Now, double check my work, and then if you have any questions, let me know. All right, good luck studying.